I am a member of IR Lab here at the University of Amsterdam, and I'm also a part of the Hybrid Intelligence Center. And I'm now a fourth-year PhD student, and I work mostly on fairness and explainability topics. And yes, let me introduce myself a bit more. So I started actually studying math in Freiburg and Utrecht, and I did pure math, mostly geometric stuff, some algebraic stuff. And also wrote my thesis there, but once I was done, I saw that the field of math is progressing very slowly, while there's AI progressing super quickly, and there's a lot of also problems with AI, right, that need to be addressed. So I decided to move on and actually try to teach myself programming, and I worked with startups at some point, I thought, okay, I really liked academia, so I went back to academia and started my PhD here with Martin de Rijke and Abhishek Anand, who is going to give a talk later today. Can we do something about the feedback? Okay, I will just continue. Yes, so... Because of your sound of the phone. The phone? I turned it off.
No.
Yeah.
If you put the device in your backpack, the one that's in front.
This here?
Yeah.
Oh. Thank you, Harry. Okay. Yes. Okay, and now I work mostly on biases and information retrieval, fair ranking, and also now explainability topics. And yes, today we will talk about fairness, and I want to open up with some headlines from the markup. The markup, they do investigative journalism into, big tech, for example. They try to uncover things big tech do and might want to hide. And you can see here a few headlines, right, that might be, shocking or problematic. Like there's mortgage lenders that, seem to use, give different mortgages to different people with, where they, maybe take things into account, like maybe race or gender or whatever that we would not want them to. Then we have here Google, who allows advertisers to not show ads to non-binary people job ads. We have Facebook, who had apparently a racial ad category where they would profile people with respect to race and put ads on their page with respect to that. And we of course have Google that puts only Google results on the top results when you search something, and say you can scroll down, right, and find other information if you really want to. And all of these topics, they touch on fairness questions, right? Is this fair? Should we do something about this, or is this fine? And this is exactly what we will talk about today also, about what do we consider fair in terms of, for information retrieval, in terms of ranking, and what are things maybe to look out for. And yes, let's start talking about objectives in IR. Usually what we want, or what maybe someone who builds a search engine or recommender system wants, is just to provide the best results for the users. So, and what are the best results? Well, the most relevant results, right? So there's this very popular probability ranking principle that says for optimal retrieval, documents should be ranked in order of the probability of relevance or usefulness. And that sounds very plausible, right? We just gives the user the best experience, the best results. But in practice, we might also care about other things, right? We might care about diversity, not only, maybe even for the sake of the user, right? If you only see the same kind of document every time over and over again, that might not be actually what you're looking for. You might want more diverse results. We also care about the items that are ranked sometimes. So actually the search items, right? So I will come with a few examples in a second, but we also might care about user fairness. So you don't want to only provide good results for the majority group of people. You want to provide good results also for people from minority groups, that might have a different search intent than the majority being passed. So examples where we might care about the searched items would be, for example, finding a local business. So think about a Google map search where you look for a restaurant, right? And actually whether a restaurant shows up on the top of the list if you look for a restaurant in that area or not really impacts the success of the business success of that local business. Then like purchasing a product or a service, like on Amazon, let's say, there it really matters for you that you are a retrieval, that you can be found by people if they look for you for the kind of product that you're selling. Recruiting a candidate for a job, right? That's very important. If we think about a recruitment search on LinkedIn, where recruiters look for people that they might want to interview. If you never show up in these results, or if you only show up on the bottom of the list, you will have significantly less career success, probably, than people that show up on top of the list every time. And so there's more examples, right? Discovering events for groups to join, learning about the political candidate, dating as well. So all of these cases, we should not only think about the utility for the person that looks at the ranked list or like the recommendation. We should also think about the searched items and how can we make sure that they're treated in a fair way. So today's focus will mostly be on fair ranking. So that means even though a lot of the methods and also definitions that I use or introduce can also be used in the recommendation context. We're not going to focus that much explicitly on this. I will also not talk that much about bias in LLMs, although that's a big source of bias where it comes from, but we really focus more on if there is this bias, what can we do with that? And same goes for diversity. It's very related. A lot of the methods have some intersection, but we will not focus that much about this today. Yes, so let's start with an example. And with this, I hope to, to explain what we mean with fairness in the field of ranking. And this is a job candidate example. So these are these 6 people, and they are all looking for a job in the same field. And now, if we talk about AI, right? So we want to train a model to predict how relevant are these candidates. So we need data for that. And the way we collect data can be different in different ways, right? We could have like a relevance judge. So there we ask the person, maybe an expert recruiter, to rate different candidates, to say how relevant would they be to a certain job, and then you can train on that data a model that can predict these, like the relevance automatically. You could also have clicks, right? So you can have, like, for example, if you think about LinkedIn, there's a lot of data from recruiters that click on different jobs, that click on different candidates for their jobs, and you might even have information about who they interviewed and who not. And so with this data, you can then train a ranking model, right, that predicts for also new candidates, how relevant are they. And I have an example here. And so we see there's something interesting happening here already, where the ranking model seems to think that one group of candidates, let's say this is the male group of candidates, right, has a slightly higher score on average than the other group of candidates. And I would like to just poll on like the feeling of the group here, well, what is fair and what not. I would like to poll here, like with a show of hands, who thinks this is a very big bias and we should definitely do something about this? Or like maybe others think the bias is maybe there, but we can't really tell it's a very small bias and we might not have to do anything about this yet. So who thinks we should definitely do something about this bias? Okay, few people. Who thinks, I'm not sure, maybe we should do something, but we should investigate further and see. Okay, I see a lot of more hands. Okay, now I will, of course, like just looking at the scores is not enough. We have to look at what do we do with this, right? Because in the end, we want to present a recruiter with a list of candidates. So here now we have a ranked list of candidates, and following the probability ranking principle, we have ranked all the male candidates on top because they were predicted as more relevant, and on bottom we see female candidates. Another show of hands. Who now thinks this is unfair and we should definitely do something about this? I see more people. Who thinks this is still like, yeah, this is just how the model works, and I think, whatever. Okay, thanks for the honesty. There's still a few people that are not convinced that we should do something about this. Now let's look at the exposure distribution. I'm not sure if you've seen this before. Harry, did you? No, okay. So this is the way that people look at a ranked list. Usually, like you start at the top, right, and you look at the first item, and you look at the first item maybe in more detail, and then if you haven't found whatever you want, you go down the ranked list and you spend less and less attention on these items on the bottom. So this is what we call exposure often, and what we take into account if we talk about fairness, right? Because we would like each candidate to get a fair chance to be exposed to the user. So this leads to something like you can see here, where you have like a very small difference, right, originally in the relevance of the candidates, but because of this exposure distribution, the amount of exposure that the group of the male candidates gets is much bigger than the exposure that the group of candidates of female candidates gets. So because of this way of how we look at a ranked list, we amplify this bias that was there beforehand. And that really highlights the importance in ranking or in information retrieval in general to consider these fairness issues, especially like maybe more than in other tasks because we have this amplification of biases here. So, well, what we can do is we can say, okay, we take a little bit the fairness into account. We want the groups of females to have the same, or it's roughly the same exposure as the group of male candidates. So we just swap around a few of the candidates while still trying to keep utility as much as we can. And we will get something where the exposure, the ratio between exposure and utility is roughly the same for both groups. Okay, so who would think this is now more fair than before? Yes, okay, great. So this is our first goal of fairness and ranking. So here I try to define fair ranking and then following chart over here. And so we say a ranking is fair if at least, right, there is enough sufficient presence of items belonging to different groups, particular groups that are disadvantaged or protected, we also call them, right? And with this we avoid the statistical discrimination or like also allocative or distributive harms. Okay, that's the first point that we consider in fair ranking. Now, like maybe a different perspective on this, now we, instead of just showing one ranking to one recruiter, we show a lot of rankings to different recruiters that all look for candidates in the same field, let's say. And now we have determined that this is a fair ranking, right? So we show the same ranking to each recruiter. Again, a show of hands. Who thinks this is unfair? Okay, I see a few people. Oh, wait. So, like, why I would agree that this is maybe not the fair thing is, well, if you show always the same list to different recruiters, right? They will all go down the list in the same way, and maybe they have different amounts of people they will interview. Maybe the first recruiter only interviews 2 people, other recruiters might interview more. But in the end, right, the first 2 candidates will get a lot of exposure, while someone who is on the bottom of the list, even though they're roughly the same relevance, will not get any exposure and not get any chances. So we say this is not fair to the individuals. And so to provide more individual fairness, we would have to actually go in and provide more of a probabilistic ranking, a stochastic ranking, where we say, okay, we cannot show the same ranked list to each recruiter. We have to show different ranked lists to different recruiters, such that also people that are slightly less relevant, but still, relevant enough to get a chance, are sometimes put, on the top of the list and might get interviews. Okay, so that's individual fair ranking. So that's the second point that we would like from a fair ranked list. A consistent treatment of similar items. So, like if you have slightly different relevance scores, you should also not have too big differences in chances that you get. Okay, we go back. And now we asked a different question: is this fair to the user? And so if you just try to be fair to the items, we just talked about stochastic rankings, right? We still can have something like this, where you try to keep the utility for each of the recruiters roughly the same, so you don't try to vary too much, to tamper too much with the order of the candidates, but you say, okay, let's put, give one recruiter a very different set of people, such that the 6 candidates still gets a chance to be interviewed, right? And I hope that you guys also agree that this might not be the most fair way to do this either, because maybe actually the first 2 candidates were the most relevant candidates for the job, right? So if a company 2 doesn't get any chance to interview those and only gets like the worst candidates in a way, right? That's not fair to the user in this case, who are the companies. So we would like to have, the utility loss more fairly distributed amongst different users. So that's the 4th point. We want an equal level of satisfactions across user groups. Is there any questions so far? Yes?
So you shown us examples, you always shown us one single ranking.
Yeah.
But it might be the case that in just this single ranking, you didn't tell us anything like what was like an underlying job kind of matching for this person.
Yeah.
Maybe in this particular case, the 3 men were actually kind of better fit for this job than 3 female, and it could be not because of bias, but because of they were kind of better, perhaps in some other case. So is it fair
You're
to
right.
say that you can judge on one single ranking?
Yeah. No, I agree, right? It could just be that they match better. And this is why, this original bias that you see in the scores, we're not sure where this comes from, right? It could be that this one group is just more qualified. But what I tried to show is with this amplification, you still might end up in a scenario, right, where it's unreasonable to give much more chances to the one group. But you're right that it doesn't necessarily mean, it's not always the right choice, I think, to just say we want equal, for example, chances for everyone. And we will talk about this later also, how much fairness does a person or group deserve. Yeah, a good point, thank you. Okay, you saw that we have 4, but there's 3 missing. So far we've talked mostly about candidates and job candidates, and these are people that actually have stakes themselves in the problem, right? But what you can also have is, for example, an image search where the items don't really have stake, right? I mean, maybe the CEOs, they really want to be on the front page, and it's good for their ego, but it doesn't really have any stakes for them. So it doesn't make sense to talk about fairness here is the question, right? Because clearly we see this is from 2018, right? The search result looks different now because they actually did something about that problem. But back then, we only saw male CEOs if you Google that. But the question is, right, is there still any harm for a certain group of people if you only see male CEOs? And I have a second example here, where if you look at, if you search for unprofessional hairstyles, it's also changed slightly, but back then you could also see, a certain group of people, right, maybe black women depicted here mostly, that have so-called unprofessional hairstyles, which and on the right you see professional hairstyles on the other side. So that's clearly also not what you want, and there's clearly a big bias in there that might cause representational harms, because we see this every day. We are confronted with these ideas, and some people might actually take them like these ideas and just think these are actually unprofessional hairstyles. So in this case, even though the items don't have any stakes, we do want a proper representation of different groups. And again, we care most about protected or disadvantaged groups to prevent these representational harms. So one more thing here, where might these biases come from? Right, so it is possible that there's not really a big bias to begin with, and there's just a certain group of people that are more qualified or relevant to a query, but it could also be that there is actually bias in data where there's some, it's not really reasonable that people, some group of people gets more higher scores than others. And the first one, way the bias could sneak in is through expert-provided training data. So that's the relevance judge that you saw before. And you can think about, maybe some old person that has like still other ideas about the world labeling the data. Maybe someone has a bias in themselves, right, while they're labeling. You could think about data that was labeled previously while we were thinking differently about the world. So there's a lot of biases that can come in from like these experts that provide training data. Then you can also have bias in user-provided training data, right? We also have biases while we interact with like search engines. And if you use then this data to train a model, this model will carry the same biases that we have. Then like you can also have biases that come from the way the documents are constructed. And there you could, like there's studies that show that women and men, they actually create their CVs in different ways. There's different sections of CVs that men and women focus on. You could also think about, like in the US, like some schools might have certain courses that other schools might not have, right? Because it's like a public school. But maybe the model thinks that this particular grade for that school, for that course that does not exist in some schools is very important for the prediction of whether a student should be interviewed for a university position, for example. So yes, there's different ways where biases can sneak in, and the difficult thing is like figuring out whether there is an actual bias or not. Yes, Harry?
Maybe I'm getting ahead of you, if so, then ignore my question. But so these are biases coming from the data. But in the example that you showed with the ranking, right? If we assume those relevance adjustments are correct,
yeah,
but we still end up with that one ranking, and it's not that the data is biased, but more the way that we what we do with the data.
Right. Yeah, you're talking more about technical bias, right? So this is so here I was going more for where if we have bias in the original data, where does it come from? But you're right that even if there's no bias in the data, technical biases can create some disparities where they were not before. Yeah. Thanks for the question. Okay, any more questions? Great. So I hope the overall definition of what we mean with fairness in ranking, you got that, and you got the motivation for why we should work on that. But so now I want to talk a bit more about concrete definitions of fairness that people have given in the field, and how you evaluate for them. And yes, let's start with this example. So we're going to start talking about probability-based fairness definitions. And here you see an example of Xing search. I think Xing is also like some career, like matches candidates to recruiters, or like, yes. So and then you see here, right, on the left, you see different professions: economist, analyst, and copywriter. And here you see gender labels again. We use gender a lot because it's like an easy. I mean, usually that's another problem. It's always binary in these data sets. So this is one an instance where maybe we moved on to like more fluid definition of gender, but the bias in the data for binary gender is still there. But so for this example, we only look at binary gender, and we see here for economists, mostly male candidates are recommended, right? For analysts, we have mostly female candidates. And so you have this distribution in the top 10, and then we have the distribution in the top 40. And you actually see that it's not the same, right? So in the top 40, the candidates seem to be distributed much more equally than it seems like in the top 10. So this the idea of this probability-based fairness is that because we have this distribution, right, of like how many candidates are there at all for this job, right? This should be somewhat reflected in the top 10 also. This does not take into account, right, that some candidates might be more qualified or not, and this might be correlated with gender. This specific definition really focuses on we want a certain distribution to be represented in the top K. Right, and probability-based fairness now takes the idea of let's assume we have a fair ranking, right? Let's say the hypothesis, the zero hypothesis is this ranked list is fair, and then we look at this other ranked list that we have, and we have to decide: do we have to reject the hypothesis that ranked list is fair? And so how we can do that is we can define a probability distribution of fair ranking, basically, for fair rankings, basically. So we say if we decide what would be a fair share of people or fair success rate for a certain group of people. So that's a success rate P maybe. And that could be, for example, if you look at back here, it could be the share of female candidates in the top 40, for example. Right? And if you say, okay, this is 30%, so I would like with 30% chance for women to be sampled at each position of the top K. And you can now sample a lot of different ranked lists that are all sampled from that distribution where you sample women from 30% probability. And yeah, so we have defined this share. And now you say, okay, the ranked list that I have here is fair if it's from that distribution that I just defined with a probability of, with a certain probability, right? So you can say, okay, I want to be 95% sure that this ranking is not fair to reject it as a fair ranking. And yes, so you can do that for every prefix. So you say, okay, I look at the top 10, top 20, and so further, and look at is the list fair for each of the prefix, and reject this ranking as fair ranking if this doesn't hold. Yes, please.
So I have a question.
Yes.
I have a two-part question. First part is what is the cost of fairness? So I'll ask this question with a very specific example. So let's say you have a system of recommendation system, and there are like categories which are like high impact categories and low impact categories. And there is a situation where you do want to be fair to low impact categories, but to be fair to the low impact categories, you're impacting the performance of high impact categories. In those kinds of situations, there is a cost to fairness.
Yeah.
And number two, the second part of the question would be how to define where we should be fair. I'll give another very specific example. I don't know if you're familiar with the Gemini cloud, right? So basically what happened was Google, when they came up with this vision LLM, people were searching for Nazis in Nazi Germany, and then they showed some black people there. So just to be fair to black people, they showed black people in the context of Nazis.
Yeah.
So question is, where should we be fair?
Yeah.
And there's a cost to fairness.
Yeah.
How do we evaluate that?
Okay, I will repeat the question so that people back also. So the first question was there is a cost to fairness, right? So usually what you see is if we correct for fairness, so if we want to make push up certain candidates, for example, in a job interview setup, we will lose utility. There's a cost to it, and that is true. If you just look at the utility the predicted utility or like the measured utility, you usually see this trade-off, right? And then you will see some plots later where you actually see the trade-off. My answer to this usually is what we measure is not necessarily what we really want in the end. Assume that there is actually a bias in the data, right? What we measure is like containing that bias and if the candidates were actually equally relevant, we are actually losing utility by not ranking the best female candidates with the best male candidates. So, but it's true that in theory, if we just assume that the given relevance labels are correct, we would lose some relevance. So it's a difficult decision, and people look at trade-offs, right? How much utility is acceptable to lose for the cost of fairness, and there's no real answer. Not one answer, but I guess in the end, if you want to increase fairness in a company, you will get a budget of how much utility you can use. So that's right. The second part of the question was where, who decides what is fair,
or where to apply fairness?
Where to
Because
apply
you
fairness,
cannot apply fairness in every single situation.
Yeah.
For example, the
Yeah.
Gemini example that I just gave.
Yeah. So that comes to a criticism on the field that I will have later, which is who decides what's fair also? We are computer scientists, right? It's not like, maybe there is some social scientists in the crowd, that would be great, but most of us are computer scientists, and of course you can read literature about what's considered fair in social sciences, but
my question
yeah.
is a little bit different from
Okay.
the question that you asked us.
Okay, yeah.
So who decides what's fair is also very important because
Yeah.
Facebook recently.
But you inside.
But there are some fairness where the factual fairness is missing. So we know for a fact that black people were not Nazis.
Yeah.
So you cannot show black people as Nazis
But still,
because it's just not factually correct.
So what I want to get to is, I also cannot answer that question, right? Should we put black people in images of Nazi because we want to be fair to black people?
Exactly.
Obviously, I would say no.
Yeah.
but there's probably more nuanced examples, right? Where I would be I don't know. And I think it's a difficult question, and probably something that we should sit together with ethicists, with social scientists, with historical scientists, what have you, and come up with answers to that. The problem is that this is usually, I think, not done. And people make the decisions of what should we make fair and what not, that are maybe not the most qualified for that. Okay, if we already have questions, are there other questions now? Okay, then let's move on. Okay, so this probability-based fairness really looks at how likely is it that this ranking is sampled from a fair distribution, basically, right? And how we can evaluate for this is we can look at a function that measures how well the share of protected attributes in a top 10 or top 20 or whatever agrees with a fair share that we defined, right? Here you have just a simple difference-based definition, and then you can measure, you take some sum over different prefixes, right? You have here a discounting factor for the 1 over log 2i, where you say I care more about the top 10 than about the top 100, and a normalization factor set here. And this is a very simple metric that you can use to have an estimate, right, of how fair, or maybe more compare how fair different methods compare with each other. Yes?
Just one question.
Yeah.
These are permutation or combinations where maybe sigma
Right. Good that you asked. I didn't find it. Yeah. So sigma is a ranked list. So like it's basically a permutation, right, of the documents. So one certain permutation that gives you the ranked list in the end. Does that make sense? Yeah. Okay. Thanks for the question. I forgot to define that. Yeah. Okay. So this is probability-based fairness, but then also so far we only looked at a single ranked list, right? So I only talked in the introduction about stochastic ranking policies. So let's define these here now. So for some fairness requirements, it's not enough, right, to just have a static ranking. So we want to have a probabilistic ranking, or stochastic ranking. And so this pi I define as a stochastic ranking policy. And you can think about this as a probability distribution of a lot of different ranked lists, right? Or maybe all possible ranked lists. And in the end, the ranked list is just a permutation of the documents, right? Yes, and then because now we have a whole distribution of the different ranked lists in our policy, we need to think about what is the exposure now, and what we use is expected exposure, which works by integrating over like this whole distribution and just taking the expected value of the exposure for all ranked lists that are possible. Yes, and then like we immediately want to define the group exposure, because we usually or often want to consider groups, right? And there we, in this case today, we just say the exposure of a group is just the sum of the exposure of all documents in the group. And you can also take the mean. There's like choices here, and none of the choices is perfect, but like for now we just take the sum, and we will later like also take the sum of the relevances, so that cancels somewhat out this choice. Okay, so let's come to fairness of exposure. Fairness of exposure is really considered with how much exposure, rather than like the prefixes that we saw before, it's considered with how much exposure is a document or a document group getting. And the first definition that I want to talk about is demographic parity. So there we say two groups, right? They should get roughly the same exposure, maybe the same size. Maybe you also say, okay, the exposure of the one group divided by the exposure of the other group should be equal to a certain share that you defined beforehand. It could be, you know, the share of candidates that even apply for the job, something like that. So demographic parity really just looks at, like, defines a certain share of people, like of exposure that you think one group should have over the other. Any questions on that so far? Good. Then it's not also, so that comes back a bit to the question here from before, where like you might not want always to give like the certain share that you defined before to each group of people. You might actually want to make this dependent on how much the group deserves. So we have to define how much exposure does a group deserve, and often you use utility as a proxy for calculating how much exposure does a group deserve. So you define the utility of a group as the sum of over the utility of all groups, and it's called as merit. And there's other definitions of merit where you take other things into account. But we will just use this definition and say, okay, the relevance of a document really says everything about how much deserving the document is. Does that make sense? Okay, good. Okay, then with this we can define more of a merit-based definition of fairness, which is disparate treatment, and which says a policy is fair with respect to disparate treatment if the exposure utility ratio or exposure merit ratio for each group agrees with each other, right? So if you get, like each group gets exposure relative to its merit. And here note, like we can also make this individual fairness definition by just using groups of size 1, right? And then we just require each document to have exposure relative to its relevance. Now this maybe sometimes it's also not the right answer, because how much does it really help a document or a document group to be exposed if nobody's ever going to consider these documents because they're irrelevant to the query, right? Nobody's going to click on the documents, so they're not going to be bored. Nobody's going to invite these candidates for interviews because they're not relevant to the position. So for this case, we consider, rather than just looking at the exposure, we consider the click-through rate or some other metric that measures how much actual impact is there on the group of people. So yes, with the click-through rate, you can do the same. You can say, I would like the click-through rate of each document group to be relative to the merit of the document group. You guys, you have heard about click-through rate before, right?
Clicks by impressions, right?
Sorry?
Clicks by impressions.
Yeah, okay, good. Yes, so that focuses more on the impact of each group. Right, so these are all different nuances of kinds of exposure where you really take into account how much exposure of click-through rate you get. Yes?
So I have a question to this. So again, like in the previous lecture, we talked about relevance and right? So if you, CTR is not really a true proxy for relevance, and some of it is due to the MNR problem, missing or where an item is not popular and due to some positional things in the search ranking page, SRP, search results page, you might not see an item not getting clicks even though it's there just because it doesn't capture the attention of the user, but if you do promote it, it will get it.
Yeah.
So there is an opportunity that is not quantified in user interaction.
Yeah.
So in your previous equation, when you do have the exposure, that exposure might not, CTR might not be a reflection of potential exposure that you might be getting if, let's say, a query or an item which is less popular, if it was to be here, get it, which is not there in the single data set that you're doing.
Yeah, so you're thinking about training on clicks,
Yes.
clicks, right?
Right.
Yeah, yeah.
Even if there is no data, let's say,
Yeah.
for example,
Yes.
then when you do these kinds of measurements,
Yeah.
the
Yeah.
potential exposure is unknown in certain cases.
Right. So let me explain. Because we try to measure or define, right, what would be trend. So what we assume is we have this rank list or the ranking policy in place, right? And then we can measure how many how the click-through rate is for each group.
That's empirical.
Yeah, I mean that's the idea. It's more theoretical here, right? So, but in the end, you want to measure, which I will talk about this. So then you would assume that you have something in place, right? And you can measure the click-through rate and compare the click-through rate between different
positions.
between different groups, right? We are more interested in the groups or the documents.
But my question is that how do you know if a document, let's say fourth position, you have the click in one group, and third position you have the click rate, fourth place or whatever. I mean, if let's say the document was promoted to first place, might get a different document might get one place. So how do you guarantee that your exposure is a CTR is a good replacement for the exposure?
I mean, so I'm not claiming that maybe that's the misunderstanding. I'm not claiming that the CTR is a good substitute for exposure. What I'm saying is we might not necessarily want only the exposure, to be fairly distributed, because exposure in the end doesn't matter too much, right? You want, maybe you want rather click-through rate, right, to be equal, because the clicks are an actual signal that the user interacted with it. So the click-through rate considers the relevance to some extent, right? And so it would be unfair to just give exposure to a lot of not relevant documents from one group, because people wouldn't care. Users wouldn't care. So we would this tries to give more. This tries to give more of a fair chance of being bought or observed and actually, considered by a user, for example. So I'm not saying it's a good substitute, I'm just saying it's a different thing that we might optimize for. Okay, and then right, to measure this, because this was the definition, you can do different things, right? You can just look at the ratio of the two groups. Ratios are not that nice, right? Because you might divide by 0. There's different ways of doing this. You can multiply like on both sides of the equation with and then take differences. But like there's different ways of defining metrics like this. But the point is, we can define a metric like this and like say, okay, the smaller this metric is, the more fair we would consider this policy to be. Any questions? Harry?
Sorry if this may be not a question or comment, but so Singh and Joachim's make the argument, right, that CPR is more what you really want, right, the action. And I agree with their argument, like I think it's fair. But I think it should also be noted, which they don't, is that you could also make the opposite argument. Because let's consider an example where the people that are clicking, or hiring someone, right, on website LinkedIn, are discriminatory. So they won't click on some group of people.
Right.
Now if we optimize for CPR, we're going to say, well, these people never make a chance anyway, so we remove them from the ranked list, and these people would now sort of live in the bubble that they want to live, which doesn't reflect the diversity of society, but just their discriminatory preferences.
Yeah.
So that would be an argument to go for exposure instead of CTR.
Right. So my answer to this would be, did everyone get the point of Harry, or should I repeat it? Okay, good. And so my answer to that would be, if you present a ranked list to people that don't want to consider a certain set of candidates anyways, right? It doesn't in the end matter if you like show these candidates further on top or not, right? So it doesn't really matter if you consider maybe click-through rate or exposure that much. I mean, you will have a really hard chance to optimize for click-through rate there because they will just never click on the people. So I would argue, but yeah. So I think like these people that want to live in a filter bubble, right? I think it's very difficult to make present them with a fair ranked list because they will just reject whatever you present them with. So I agree with your point. Right?
I'm not saying that there's an answer, but maybe to point out your own slides that the example where you look for CEO and you only saw men, we all are like, that is clearly a problem.
Yeah.
Now, if there are enough people online who are doing that search that don't see that problem, should we now no longer consider it? I don't know, it's complicated.
This goes back to the question of what should be fair, made fair and what not, and like should we take people into account, like their preferences, right? Should we accept filter bubbles, should we accept biases that people might have and just present them with what the results they want to have?
Yeah.
I think these are good questions, and I also think click-through rate might not be the perfect thing to consider, right? Like the impact, we're just trying to make a kind of proxy for the impact, right? So I'm sure there's also work on how to do that better. I hope so. I'm not aware at the moment, but yeah, it's a good point. Thank you.
Yes, and maybe good to know for students is that when this paper was published in, was it Heuss or ESSIR?
I'm sure.
So people, they often are not encouraged to critique their own assumptions in the paper, so you have to, you only see the one side.
Yeah, that's true. Okay, one more metric to measure the spans of exposure, because as I mentioned, these are not really perfect. So another suggestion here by Diaz et al. Is to think about the exposure in terms of a vector, basically, and say, okay, I define the vector of exposure where I have all the groups, and for each group I have one entry in my vector, one dimension in the exposure vector here, that's epsilon. And I also define epsilon star, which is the ideal exposure. Right, so exposure that in a perfectly fair ranking each document group would get. And so you can calculate this, for example, if you have disparate treatments, right? You calculate how much share of the total utility does one group have, and then you multiply this with the total exposure that is available. And then what the EEL, expected exposure loss metric, does is it takes these two vectors and it just calculates the squared Euclidean distance. Don't ask me why the Euclidean distance, because to me it doesn't make, like it's a choice that you have to make, but it's not necessarily a canonical choice, but this is what the authors came up with. And I think what they highlight here, what's nice about this is there's, here I can point, oh no wait, I actually have this, yes, oh sorry. Yes, so here, like we have this one factor in the end, right? So this is just the absolute norm, Euclidean norm of this vector epsilon star, and that's a constant. So that's the same for any kind of ranking policy you might have. So you don't really have to look at this that much. But you have here one term, which is the ED, which gives you this disparity between the different groups. So it basically says how unequally / equally is the exposure distributed amongst the different groups without really considering the merit, while this term in the middle really considers the relevance / the merit, and is also correlated with the total utility. Yes, people really like to use this metric. It has nicer properties than what we saw before. And yeah, we can determine for different policies, right, which policy is more fair with that. Any questions on the fairness definitions or metrics? And I want to highlight that this is not everything that's out there, right? There's a lot of different, nuances of fairness out there, different definitions, and also a lot of different evaluation approaches. But yes, any questions? Yes, please.
How do we know what is the perfect policy? Because we need it for the definition of the specific.
Yeah, that's a very good question, right? So if in the case where right, you have different definitions of fairness. So in the case where disparate treatment, you can just say, okay, I know the utility of each document, right? So if I assume that the utility of each document or the relevance is accurately, given, you can calculate just how much is the share of this document of the total utility of all documents. And then, according to the disparate treatment definition, then this share would be the fair share for this document. Or if you think about the group of documents, right, you calculate the utility of the group, which is just the sum of the utility of each document, and then you say how much is of a share. So that's what we need with the perfectly fair ranked list, right, which we define in the way with the relevant names that we've given. Yeah. Thanks for the question. Okay, now we're going to talk a little bit about ways of how people try to approach fair ranking, right, and increase the fairness of ranked lists. And there's different ways to do that. And for this, we're going to look at the machine learning pipeline, where we start with the data set, right? And the data set might already be biased. Might also not be. We don't. But if it's biased, we can use pre-processing methods to debias the data set. Then next step is to train a model, right? But then the model can pick up unfairness in a way, maybe also from the data, maybe through technical biases. So there we say, okay, we can use in-processing, so during model training, do some interventions to make a more fair model. And then we also, then in the end we get predictions, right? And there might still also be bias still in the predictions, maybe we didn't do any interventions so far. And so the predictions might be unfair, and that's the post-processing step where you say, okay, I have these predictions, I will post-process them such that I get a fair ranked list. And we will look at each of them independently, a bit more on the post-processing side. The other ones I will be a bit brief on, but let's start looking at post-processing. And Here, like, we're gonna start talking again about this probability-based fairness definition and how to, create fair rankings for this one. And so we talked before about, do I have to reject the zero hypothesis that this is a fair ranking or not? And now basically what you can do is for like different shares of P, which is the share of what you think a fair ranking should have candidates of a certain group, right? For each P, you can calculate what is the minimum amount of candidates of the protected group, such that I do not have to, in each top K, right? Such that I do not have to reject the zero hypothesis that this is a fair ranking test. And you will get a table like this. And so, for example, for 0.5, you should have at least one protected document in the top 4, right? And at least 2 protected documents in the top 7. And with this table now, you can design a fair rank list in a very simple way. So this was one of the first works on fair ranking, where you say, like and I'll say, okay, just rank both lists independently, like for the protected candidates or for the non-protected candidates, and then like this, iteratively sample a ranked list from there, where you say, okay, I pick the candidate from the protected group if they're either the best candidates of the whole group, right? Or we have to pick them because otherwise the ranked list will be considered unfair. So it's like you have to fulfill this minimum number of candidates of the protected group. And if you don't have to fulfill the minimum, right, you can just pick any candidate from any of the 2 lists. So you basically produce the minimum, you produce a list that is fair with at least this minimum constraint of what fairness would consider here. Any questions on that? Okay, so yes, so this is the first approach that considers more this prefix fairness. Here I promised this trade-off plot, right? Here I don't want to show this for every method, but I thought for the first one makes sense. Here we have P, right? The bigger P, right? The stronger the constraint is, the more people protected candidates you have to put into the top K. And you can really see like NCG is dropping if you increase this share a lot. But you can also see that the drop in the beginning is only rather small. So there you will have this kind of discussion with the production team what drop in accuracy is reasonable to have to get more fair rankings or not. Okay. Then we talked about the exposure-based fairness, and for this I want to show the convex optimization approach to top K fairness here. And so here we try to, convex optimization is a method in computer science. I hope most of you know it. Like you try to define a convex function, right? You have some convex constraints, and then you can solve this pretty efficiently. What you will do here is you will define a marginal rank probability matrix, and that matrix doesn't directly output, directly optimize for the policy itself, but for this matrix that just tells you with what probability each item is supposed to be placed at each position, right? I will have an example in a second, but so it just tells you with what probability item 1 is supposed to be placed in position 5 or whatever, and these are the entries of the matrix. And now you can write the utility as a function, convex function of this matrix. And you can also write fairness constraints like, disparate treatment, disparate impact, parity constraints. You can also write them in terms of this matrix as a concave function or convex. I'm never sure, convex and concave, it's just interchangeably, right? But then, and you have these constraints here on the bottom, the 3 constraints that tell you that this matrix actually tells you a probability. it's actually a probability distribution. And here we have for the top K document, so yeah, but it just tells you with what probability each document should be placed at what position. And now we can solve this for example, a disparate treatment constraint, and we will get this matrix, right? And now, to get from the matrix to a policy, we still have to say, right, for different ranked lists, how probable they are to be shown to the user. So you decompose the matrix with what's called the Birkhoff von Neumann decomposition. And I have an example here of how it would look like. So here you can see the marginal rank probability matrix that you might get as an output from this convex optimization problem. And here you can see, for example, the first entry will tell you document 1 is supposed to be placed with 0.2% chance, with 20% chance, sorry, on the first position, and with 40% chance on the third position, and with 40% chance on no position, right? This is a top 3 ranked list. And then you can decompose this into like different rankings, right? These matrices, they are what we called sigma before, so these are the ranked lists. And like this, you get a probabilistic policy that tells you for each ranked list how probable should it be that it's presented to the user. So this is a way how you actually get to a stochastic ranking policy that fulfills these constraints. Yes.
So basically, if I'm understanding what you just said, you show different ranked lists to different users or users in a different time.
Yeah.
Every single time.
Yeah. So imagine again if you have like this talent search that we had in the beginning. You could have different people looking for a software developer that maybe develops mainly in C++ or something like that. Right. So you have like the same query that this gets issued over and over again, and that doesn't really work for every. Like obviously for each query you need its own policy. So that's like a downside for that. But if for queries that are issued very often, you can come up with these probabilistic stochastic policies. And that make the thing more fair. Yes?
Sorry, how do we know that the constraint matrix, the policy fair, is convex? So if the problem is both?
Yeah. So in this case, it is. You can express this as a matrix multiplication with a P. Yes, so, but if you're interested in that, let's discuss this after lecture, because this goes a bit into too much detail now. But good question, yes. Okay. Yes, so with this convex optimization approach, now we optimize for item fairness. You can also think about two-sided fairness in the setup, which is what we discussed in the beginning, that you don't always only want to be fair to the items, but sometimes also to the users, and they ensure that the users don't, like certain users don't get all the utility loss, so basically just for the sake of fairness, a lot of irrelevant documents get dumped into like one group of people that's less relevant or something like that to the machine. And so for this we need two-sided fairness. And yes, so the goal is to distribute this loss in utility more fairly amongst users, right? And for this, like consider that different users might have different intents, right? So maybe a minority group, if they look for, hairstyles, let's say, or even for jobs, they might look for something slightly different. That could be a reason for like a disparity in the actual in the utility between users, but you could also think about what I just discussed, right? That the loss in utility is unequally distributed. And for this, you can define this utility for a certain user group that rather than take the expected value over all the users, it takes the expected value of this exposure times relevance over just the users of the user group. And with this, now we have right, this utility of a user group, we can aggregate this to get like one number that gives you the utility of more fair, you know, the value for the utility for different users. And here you see that we, instead of just summing over all user groups, we have this, we sum over the log score of the utility. And the logarithm, right, this has diminishing returns. So that's the idea. If you have one user group that gets like a perfect utility, but one gets very little, the one that gets very little utility will just weigh more relatively. And then you can weight this with this factor P here. You can use, for example, use the group proportions to just make sure that not, you know, if you have a big group, it doesn't carry any importance anymore, how much utility this gets. And with this, you can take this convex optimization approach again, and you can say, okay, just maximize this new value for the user utility under the constraints that we had before. And you can also have this item fairness constraint, right? And with this, you can get the two-sided fairness. Any questions so far? Great. Then, yes, I promised some in-processing and pre-processing approaches. Maybe I'm going to jump over the pre-processing, but let's briefly talk about in-processing. So, yes, why? The question is, first question is, why do we need in-processing approaches? And I have two reasons here. I'm sure there's more, but the first one is there's this law which is called European General Data Protection Regulation, which tells us that we cannot record or also use protected attributes of certain kinds for algorithmic purposes. And these categories of sensitive attributes would be things like sexual orientation, race, religion, like all these things that we might actually want to consider for fairness approach, right? So if we don't have them, we can't really correct for them in a post-processing way, right? Secondly, also in-processing approaches can be more effective because you already taking into account fairness while you train the model, so the model sometimes can be trained more efficiently for fairness and utility at the same time. So the plug-and-loose ranking policy is another probabilistic policy, and this is one that you can actually optimize during the training process. So how this works is you have a model M, and this trains to predict a log score, right? And then what you can take these log scores and generate a probabilistic stochastic policy by saying, okay, the probability that I will pick a document at the position K for a ranked list that is already a K-1 ranked list, you see here, right, is given by basically the softmax of the softmax distribution of the remaining candidates that are not in the top K yet, or top K minus 1. So what you do is you iteratively sample documents, right, and you sample them relative to the score, so the squared log score, basically. Does it make sense? It's a bit maybe difficult to wrap your head around. Okay, I see some nods. I hope it makes sense. Okay, but then like this, you have this probabilistic policy. You can also calculate how likely a certain ranked list would be, right? You just calculate the probabilities, you just multiply the probabilities iteratively towards each other. And yes, to just have one example here, how this would work, right? So we have these log scores here predicted, 1.5, 1/4, 1/4, and now we start by sampling one document. Let's say we sample document A, right? And then we calculate basically softmax score over like with all these log scores, and we get probability of A being at the first position is 1/2. And then we do the same for B, so then we remove A from the pool of candidates, right? We only have 2 candidates left we can draw from, and we can calculate now this ratio again, and we get again 1/2. the remaining candidate will automatically be sampled at the last position, and we will get probability of this ranked list to be 1.5 times 1/2. It's 1/4. And then, like other ranked lists, you can do the same, and you get this distribution of all ranked lists. And yes, so you train this model, right? You have to make sure that you have differentiable fairness laws. And I mean, with anything differentiable is a challenge already in information retrieval, right? Because we have these ranked lists, and ranking is not a differentiable function. I'm not sure if you've heard about this.
No, actually, there are some differentiable NTGC loss functions.
Right. So, like, you have to use a lot of tricks. A lot of tricks, and the same, like, Heuss would be here as well. Also, these policies are really difficult to optimize because you have a lot of sampling. And actually, Harry did a lot of work there. You can ask him if you're interested more on that. But yes, so to train this very efficiently, you have to use lots of tricks, but it can be done, and you can include this fairness loss in your model training, which is nice because you don't have to use post-processing. And why this is nice in terms of this data protection law, is that you can work with donated data basically. And here, Clara actually can tell you more, who's working on that later if you're interested, because they're like, right, you can try to kind of build an artificial data set where you do know the labels and then train on them and use that in the end to try to have a fair policy, even though during inference you don't know the relevance labels. Exactly, and then you can also use like a trade-off factor, right, to tell how much weight you want to put on fairness, how much you want to put on utility. So there's again a trade-off happening here. Usually, I guess you use fairness as a regularizer of some sorts. Questions on that? Okay, then very, very briefly, the pre-processing. I'm also not that aware of like the newest developments here, but the idea is basically, okay, if you have bias in the data, can you debias the data in a way? So, for example, you can try to take data and make it in a way such that you cannot extract or classify the protected attributes from the data anymore, right? So you try to remove all the impact of, for example, gender that gender has on the prediction in the end, or even like on any kind of prediction. So you cannot extract the data from there anymore, the gender labels, and yeah, like this. And yes, it's a good way, right, to remove bias if it's there in the data. Sometimes some people try to also just leave away protected attributes, but then you realize that they are correlated with other features, right? So that's not really enough. So you really have to come up with a new representation of your data in a way. But yeah, that's I'm not super aware of that research, so we will just move on. And talk a little bit about the last, so this is the last chapter of this talk, where I want to talk about more newer research, newer developments, and I want to focus on assumptions that we're making here and limitations about these assumptions. And assumptions that we're making are a few. That's not the only ones, but these are the ones that I want to highlight. So first of all, we make assumptions about the relevance scores, right? Because for this metric-based utility / fairness definition, we use the relevance as proxy, but then for this we assume that we actually know the relevance of each document, which would be great, right? Because we could produce perfect ranked lists and we would be done. But in practice, we don't have the perfect relevance of each document. We just have approximations. And not always are these approximations very good. And they're also not well calibrated. And I will talk about what I mean with calibration in a second. But that can be the first problem in identifying even how much merit does each group have and how much exposure they give each group. Then we assume that we know all the protected attributes of all the candidates, which is, as we saw, right, sometimes you cannot record this, but even if you can record this, maybe some, like in the US, I don't think they have this law, so they can actually record, gender, sexuality, what have you. But you might not always be confident in telling everyone about that, right? Maybe you leave this field empty, right? If you have a sexual orientation that you're worried about that people might discriminate against. So there is not at random missing data on the protected attributes, which can be a problem as well. And then we also assume that we can estimate the exposure accurately, because the exposure is like what most of these methods were focusing on, right? Distributing exposure accurately. And I want to start with showing you why this does not always hold. And this is our own work, actually. So here you have two different ranked lists. This is a product search where smartphones are searched for. And on the left, you have a normal ranked list. On the right, you have an outlier, we say. So it's a visual outlier that looks slightly different. It has some text, it has some colors, some bold letters, and so on. And the third document. And if you look at how the exposure is being distributed amongst these documents, that's an eye tracking experiment again. And you see, like, this exposure distribution of the outlier list differs a lot from the other one. And like this is for this one, we usually assume a position-based exposure distribution. So that's also like an assumption that is heavily used in learning to rank. But for the right one, we don't really know the exposure, because outliers in ranked lists is not a phenomenon that has been investigated that much. So there's now some research coming up, but it's not enough to really tell how does the exposure look like. And there's more examples of this where you could think of similar documents being placed above each other, where user focus more on the first document rather than the second one. And so the question is, what can we do about this? Because if we just, we want to ensure that the fairness is equally distributed, but we don't know the exposure is equally distributed or fairly distributed, but we don't know the exposure. So what we came up with is saying, well, if we cannot accurately approximate the exposure, let's try to avoid this that have a different exposure than the user model. We assume, so here on the left you see two ranked lists, right? And they both have this problem that they have similar documents ranked in the same list. So exposure distributions look different. Well, we can just shuffle these candidates along the ranked lists and get two ranked lists that don't have that problem. That's the idea. So yes, the solution is, because we have the probabilistic policy, stochastic policy, we can make use of that and just shuffle around, create different policies, because there's a lot of different ways to create these policies, such that these documents do not show up in a context where they're considered outliers. Yes, but there's a lot of open questions, right? So avoiding these ranked lists is kind of, computationally expensive. It's maybe not what you want to do in practice. Maybe this is more of a proof of concept, right? So, but can we not maybe design better user models to account for this shift in exposure rather than avoid it? Also, there might be other phenomena that we're not aware of, right, that impact the exposure distribution. So there's a lot of open questions about this. Yes, but let's move on to the second challenge, which is the unknown protected attributes. Here I have again this data protection law that prohibits you from recording things like ethnicity, religion, health, sexual preference, right? And so you do not have in Europe labels for protected attributes. And even if you have them, I argue you have noise, they might be very noisy. Right, so we can use pre- and in-processing methods for that, potentially. But you still need these protected attributes in the training set, at least, right? And that can also be a challenge. You might have very artificial training sets and so on. So one solution that you could think of is, well, if we don't know the protected attributes, can we not predict them? So maybe you think, okay, I know the name of each person, can I not predict ethnicity, for example? And people have tried that, and it turns out it's not really good. You cannot really predict just from the name, also from images, for example. It's very difficult to predict the ethnicity. Also the gender is very difficult to predict even. And you see also here a big bias, right, towards like people are more often predicted to be white than anything else. So if you use these inferred group labels, they might actually cause more harm than good. So that is recommended against. There is some work on fair ranking with noisy protected attributes, so more recent. But so there, the authors assume that the protected attribute is a random variable, and they say, well, we want the constraint to be approximately satisfied. Yeah, but they do assume that the labels are missing at random and are independent, which I just tried to explain that there might not be, right? There might be actual structural differences and how labels are missing. So there's here as well, I want to highlight that there's a lot of work to be done here, and I think this will be a very important field of research in the future. It might be something interesting for, you know, starting PhD students to get into. How do we work when we don't have protected attributes, if we maybe have only a small set of protected attributes, or you know, if there's a different shift, a different distribution of protected attributes and the training data versus the test data. Okay, and then the last challenge, uncertainty in the relevance prediction. So yes, most work on merit-based fairness just relies on this relevance prediction, right? That and assumes we know the relevance of each document, or at least we have a very good approximation of this. But we also know that this relevance prediction carries a lot of uncertainty. Models are also very overconfident in their prediction. And the scores, because we train with list-wise models, are not very well calibrated. So what I mean with calibration is, we usually assume, right, that for these fairness definitions at least, that we have that the scores, the ranking scores, reflect the probability of each document to be relevant. While in practice, if we train with list-wise or pairwise scores, this does not actually predict the relevance, it just predicts a score that only has meaning in relation to other scores. So we cannot really easily get the probability of relevance from that prediction. And people have tried things like min-max scaling, which is obviously really bad, right? You just say, okay, the best document has probability 1 of being relevant, the worst document has probability 0 of being relevant, but there's no really grounding in like how you should do that. So what you would like is a list-wise ranker that also predicts well-calibrated relevance scores that are actually aligning with whether a document is relevant or not. And actually, fairness is not the only field where we would like that. There's also, I think, you know, for click models that would be really beneficial, a lot of areas, but we don't have a solution for that. So that would be a really good direction to look into more as well. Like, how can we calibrate predictions from this wide ranker? Oh yeah, and I wanted to highlight that the uncertainty that a model has on the predicted labels also doesn't necessarily need to be fairly distributed. So here we have two groups, we have group A and group B, and the model potentially has seen a lot more data for group A, right? And it can make very certain predictions about group A. While for group B, it has very high uncertainty. So there it just predicts basically random scores and says, okay, but scores have very, you know, very broad probability distribution. We're not really sure about these scores. But if you just use the scores, right, the mean scores, what you will end up with is a bias, as we saw in the beginning, right? And this can be a potential source of these biases, where you say, I'm so uncertain about the probability of some groups because I have so little data on them, or they have data missing, not at random, that like we just basically give random scores to them, and which can cause a big disparity in the actual chances that these candidates get in the end. Yes, and there is also some frameworks that try to take into account this uncertainty in the relevance prediction. So here, this is Sin et al., and they say, well, if we have this uncertainty, it should at least be acknowledged, right, and actively worked with. We shouldn't just assume that we know the relevant scores. And so the general idea of their approach is, well, if we think A is at least as relevant as B, right, they should be treated at least, with probability P, right, they should be treated at least better than B with this probability. So, right, you talk more because you don't really know. Is A more likely to be more relevant than B? You take this probability and take this into account, basically, when defining whether something is fair or not. And so they define this idea, they have this idea of approximate fairness. But yeah, there's a lot of research to be done here as well on how we can improve fairness if we don't really actually know the merit of each document, that we just have a noisy approximate of that. And as a last example, I want to tell you about one work that one of our works again, which is rather than trying to counteract or work to counteract this uncertainty in relevance prediction, is trying to use this. So here we say, okay, if we have this uncertainty in relevance prediction, why do we not make use of that? And because we have this trade-off in utility and fairness, why do we not trade off utility with fairness where we already see the model is most uncertain? So you see here on the right an example. We have 4 documents. The first one are non-protected, the other ones are protected. So we would like to increase the exposure of the protected documents. And you also see the exposure, the relevance confidence here, right, in form of these curves. And so what you can see is the model is very certain about the ranking of the first document, but it's more uncertain about the ranking of the other 2 documents. So what we say is we give this fairness approach puffer a budget of how much it can adjust the scores relative to the confidence of the model to swap documents around such that the ranking is more fair in the end. So this here you can see we choose some intervals, some confidence intervals, and we adjust the scores we adjust them upwards for protected documents and downwards for non-protected. And with this, these documents actually swap place. And we can see if we have here the relation where we do not use the uncertain model uncertainty, and we can see that the model actually can, the puffer approach can actually make much better informed decisions about where to trade off the utility if we consider this uncertainty or not. So this is just more of an outlook of what you can do if you have some, you don't know the relevance, how you can make use of that. Okay, to summarize this. We have seen that there's a lot of assumptions that we make when trying to improve the fairness of a ranking model that might not hold, right? We might not know the exposure of each ranked list. We might not know the group membership, or it might at least be noisy. And also the merit might not be always easy to determine. So I think what I want you to take away from here is we need to be aware of these assumptions that we're making, and also whether, how realistic it is that they hold or not, and when we design a fair ranked list, right? And we need to pick methods that can work with whatever we have, right, whatever data we have, but also whatever quality, for example, of merit prediction we have. So just being aware of this is very important, I think. And now, last slide, promise, some closing thoughts. But there's a lot of criticism that you sometimes read in literature where people say there's not one canonical fairness definition, and how can we even trust if they disagree with each other? And I think this is a kind of a weird thing to say, right? There's just different definitions that are based on different assumptions. So we need to know, before we pick a fairness method, what we actually want. Like, what does fairness mean for us, right? What kind of things are important for us? Do we want like the exposure to be distributed equally? Do we just want fair representation in the top K? I don't know. You just need to think carefully about this and pick the model, the approach accordingly. And yes, another point is, right, that we often make assumptions about what should be fair and what is a good definition of fairness without consulting with, social scientists, ethicists, that actually think about these problems on an everyday basis and not just have their own idea in their head of what would be fair. And I really hope that future work will show more collaboration between these fields and make sure that we actually get fair approaches that are actually useful in practice and not just on paper to be published at the conference. Okay, I'm happy to take questions also. Thanks for listening.